Welcome, everybody. It's my pleasure today to introduce Hubert Wagner, who will tell us about the slow road to fast, persistent homology for image data.
Uh, Thanks, Henry, for the introduction and also for inviting me. Um, yeah, so I mean, what I'm trying to do today is to essentially summarize roughly the last 15 years of work in the context of persistent homology computations, specifically for image data. So I had to be kind of selective in what I really talk about, but I think it should be useful. So maybe I just have two goals for this talk. I would like to overview some of the computational techniques which, kind of survived the test of time and are still being used. And I think this part is kind of maybe more relevant for people who are interested in implementing this type of software, or maybe people who work, a bit more deeply with this type of software and want to actually know how how those methods work. And on the other hand, I've been seeing that more and more papers dealing with TDA in the context of images. More and more papers like this seem to be appearing, especially in conjunction with machine learning. And one thing I see is that there is a lot of confusion about, on the computational part, often people use outdated software and then complain the computations were slow, or they just roll out their own implementations, which are often miss certain ingredients which which we developed during the last couple of decades. By we I mean collectively. And the other goal is maybe more straightforward. I just want to mention some recommendations regarding modern software you can use for this type of data for persistence computations. I'm not trying to benchmark or really describe all the available software. I'll just mention the things I would use in certain situations. So it's meant to be kind of subjective. So what do I mean by image data? I mean essentially something like this. I will focus on 3D data. So for me, 3D image data, essentially I mean scalar. Voxel data is just a three-dimensional array of voxels, and each voxel has a single value, a single number, either an integer or a floating point value. So this would be an example of a data volume with 3 cubed voxels. 2D data is more familiar. Most of the things I will be mentioning also generalizes to higher dimensions, but my focus will be on 3D data, and also this is kind of the main focus in TDA literature. And I mean, image data is a very popular type of data, very natural. It shows up it both shows up and also has topological applications, in fields like medical imaging, astronomy, all kinds of simulations, from physical, astrophysical, things like biochemistry. In one thing I would mention here is that regarding simulations, this data can also be higher dimensional. I've seen successful experiments dealing with such data up to dimension 8 or 9, voxel data. One thing which has been popular recently is to analyze the topology of intermediate outputs of things like computer vision models. So we're not really working with the some actual input data, but rather with some already pre-processed data with some intermediate step of a network. Also things like geography, I don't know, like a data representing the height of each point on Earth. You could really think about this as this type of data. An example of persistent homology on a very simple image. So this is my 3x3 image, just so that we're on the same page. When we add the first pixel, it creates, it starts a connected component which lives on forever. Other than this, nothing is really changing until we add this pixel with value 8, in which case we have obviously created a one-dimensional cycle. So in other words, we created a homology group in degree 1, and then when we add the central pixel, this destroys this cycle. So in the end, if this was our input, our output should be this list of persistence pairs in this case in degree 0 and 1. I don't really want to turn this into an introduction to persistent homology, so I hope this is enough to clarify what we want to compute. So one question I have to the audience is, we can obviously manage a 3x3 example. We just did it by hand, and my question to you would be, in terms of three-dimensional images, what kind of size could we handle? And those are actually two questions. What could we do in 2010, and what can we do currently? And you can assume like a modern, normal, regular workstation with, let's say, something like 30 gigs of RAM. So what do you think we could have done with the software from roughly 15 years ago, and what could we do now in terms of the number of voxels?
I'm hoping somebody else will guess, but if not, I'll make a guess.
Okay.
So,
Yeah, any guesses are good. Especially wrong guesses are great
okay,
in this
so
case.
100 cubed is a million, right?
Uh-huh.
So I'll guess 100 by 100 by 100 in 2010.
Uh-huh.
Yeah. And now I'll say we're two orders of magnitude better. So now we're at who do I think that? So I'm saying 10,000 by 10,000 by 10,000. That's a stretch. I don't think we're at 10,000 by 10,000 by 10,000 yet. That's
Not for persistence. But that's way more orders of magnitude, right? Someone says,
oh, I see, I see.
I mean, it's cubed, right?
Yeah, okay, so 1,000 by 1,000 by 1,000. In
Okay,
the
yeah.
in the chat, Astrid has a guess.
Mm-hmm.
So she guesses 50 by 50 by 50 in
Mm-hmm.
2010.
Yeah,
Astrid, a guess now?
yeah, I see it. Yeah, I think this is a good guess. I mean, both guesses are good. Uh, so yeah, I checked some of the literature, and yeah, something around 100 cubed, so essentially like a million voxels, was viable in 2010. It would take roughly 20 minutes and roughly 20 gigs of RAM. So most probably you couldn't really run it on a laptop at that time, but now you could. And now we can do, this computation would take 0.1 second with like a state-of-the-art GPU implementation, 1 second on a GPU, and it would use 100 times less RAM also. And I'm not really answering my question here. And we could push it to something like 2,000 cubed, so like roughly 8 billions voxels, which is like 3 orders of magnitude. So those bets were good. I mean, you had an advantage, Henry, because I think the state-of-the-art software for this, from what I checked, was actually JavaPlex.
Oh, really?
Yeah, yeah.
Oh, that's great. I mean, I didn't code JavaPlex, but I was involved in the
Mm-hmm.
tutorials, right? So I knew it was
Yeah, yeah, yeah.
a million simplices, but
Mm-hmm.
I knew that more from the RIP
Mm-hmm.
side. But it's good to have it postage stamped in 2025 that JavaPlex
Yeah,
was
yeah,
not
yeah.
always terrible coding wise as it is now.
Mm-hmm. Yeah, yeah. Things has changed, but uh, yeah. So there has been a lot of progress, and essentially, the one of the main points of this talk is to kind of pinpoint the techniques which kind of allowed this progress specifically for image data. So essentially, we want to see how you should how you could compute topological descriptors, in particular persistent homology, on image data. And the first thing is that we have a bunch of alternatives in how we actually represent the data. One of them, we can view them as a cubical complex, and then we have two options. We either interpret each input pixel or voxel as a top-dimensional cell or as a vertex, or we can triangulate it, and then we have it. And then we have a simplicial complex. So by default, for a long time, people were just triangulating, which essentially just, from the efficiency standpoint, it just blows up the representation in 3D by a factor of 3, because every cube has to be triangulated. And so from from an efficiency standpoint, using cubical complexes and not simplicial is preferred. And then those two representations, they seem different, but they're essentially equivalent. So with some extra pre and post processing, it was shown that it doesn't really matter which one you use, which is really nice, because some software sometimes uses this one, the other uses this, so it seems like the output would be kind of incomparable, but they're actually equivalent. So this is some really nice work by Adelie, Teresa, and Vanessa Robbins, and some other people who really proved this equivalence, which is something that at least in 2D people had suspected for a long time, and but it's really good to have a proof of this. Okay, so if this is our input, then we will use this T construction, which views pixels or voxels as top-dimensional cells of a cubical complex like this. But then we also need to assign filtration values to each of those faces. And then we just look at each face, look around to the co-faces, and take the mean value here. So in other words, we think that when the voxel with number 2 appears, it kind of brings all those faces along with it, which were not already present in the complex. So now we get a filtration at the level of this cubical complex. So then the question is, how can we compute persistent homology based on this cubical filtration? And I mean, this would be like a basic standard persistence pipeline that most people here should be familiar with, I would guess. So you start with some data, then you cook up a simplicial filtration, then you produce a boundary matrix, which after reducing gives you the persistence diagram, or the persistence pairs. So in our case, we'll cook up a cubical filtration, and again, we can just produce a boundary matrix and reduce it, and we get the diagram. So for now, the only change is that we switch to a cubical filtration, and this seems straightforward, but there are some very common pitfalls here, and one of them is to kind of explicitly store every bit of information about this complex. So if this is a single top-dimensional cell and all of its faces, it's kind of very tempting to represent each of those things separately as some kind of object in your programming language, and then explicitly, store links between them. So, those arrows indicate the boundary and co-boundary relationships. So everything would be very explicit. But this is very wasteful for many reasons, and maybe one of them is that those filtration values can be as small as 1 byte and maybe go reasonably to something like 4 bytes. Each arrow here, in general, you would need 8 bytes to store it as some kind of pointer or index. So already, this becomes a huge object, which already kind of bumps up the memory of of your representation. And there is a very nice trick which I've learned from Marian Mrozek, who had been working on homological computation, so not persistence but just standard homology. in the context of cubical data. And then we kind of, so a lot of the things in the context of persistence, we extended based on his early work on this. So with Chao, we called it a cube map, and this is essentially an efficient kind of succinct representation of a cubical complex, or in this case, actually a cubical filtration. So the trick is that this information here, which is this filtered cubical complex, can be succinctly represented just as an array. So we just write down all those values, and this very simple representation retains all the information. And in particular, you can query for things like boundary, coboundary, faces, cofaces, dimension of each of those guys. All of those operations can be done super fast. And so this is as efficient as it can be. You get just a single value, just the filtration value or whatever value you want to have for each cell in the complex. So in the end, you have an array. If this is your input size, then you get an array of this size. So you pay this penalty of 2 to the power of d, which in 3D would be 8. But essentially, this is the smallest representation, and you literally only pay for what you have, as opposed to like all those extra, explicit links. And at there was a time where actually where the boundary matrix reduction software got decently good. But then the first part of actually assigning the filtration values and building the boundary matrix was problematic. So this simple data structure kind of removed this bottleneck. So technically, we could do this kind of efficiently. And the next bottleneck is that this boundary matrix that we produce would be very large compared to the input size. So just as a reminder, for each cell, we just need the indices of its boundaries. So we can see how large this would be. So let's say we have n, which are w to the d voxels in the d-dimensional case, and then overall we would have roughly 2 to the d times n overall cells. So this is our number of columns. And with this, we can compute the number of non-zero entries. So this is 2 to the d times larger than the input size. And then each entry itself has to be an index. If the data is large, it will have to take 8 bytes. So in dimension 3, this the representation is bumped up by a factor of roughly 200. If we start with a 1 byte encoding of the filtration values, the boundary matrix would be roughly 200 times larger, which doesn't seem too scary. But if you really want to handle something like 2000 cubed voxels, then it would take roughly 1.5 terabytes, so 1500 gigabytes, which is not something you can handle on a laptop. So this would be the next kind of bottleneck to address. But before we talk about this, I mean, this is if you do this properly, like for example the Goody library does, you can safely assume you can do something like up to maybe 400 cubed, and maybe it will take, let's say, roughly 10 minutes. And the throughput would be something like 0.1 millions of voxels per second. And we'll see how the speed and the size increases as we add more of those optimizations.
This million voxels per second, this is the rate at which they're being sort of reduced.
So this is like an end-to-end. So if you have so it just means that that the whole computation is done at the rate of 100,000 voxels per second. So this tells you, if you have some input size in mind, you can, knowing this, you can guess how long it will take. So this is, whenever I write this, I mean like an end-to-end throughput of the entire computation, from a certain number of voxels to the resulting persistence pairs. So the next idea is to realize that most of the things we're computing are actually persistence pairs with persistence 0. So there are those kind of ephemeral pairs. So in other words, the points that normally would be plotted on the diagonal, and in most of the time in topological data analysis, you really ignore those points. So the idea is to try to simplify the representation in such a way that you kind of prune information about those ephemeral pairs as early as possible. So this can be done with discrete Morse theory. So this approach was proposed by Vanessa Robbins and collaborators in 2011. So the idea now is that instead of producing the boundary matrix out of our cubical filtration right away, we will simplify it using discrete Morse theory, and then produce a hopefully much smaller boundary matrix, which still gives us exactly the same persistence diagram. And the crux of this is really this realization that we don't really have to do much. We just need to get rid of the, of the elements of the filtration which end up not really contributing to the final persistence diagram. And it turns out that most of it is not really contributing anything interesting. And to me, I mean, I still remember when I first understood what this method does. So this was, in hindsight, this is completely obvious that you can do this, but I was completely shocked that something as simple as this will, can make such a huge difference. And we had been, I remember for a couple of years already, we had been thinking about how to use discrete Morse theory in the context of persistence, and it never crossed anyone's mind, of the people I talked to, that that this is what you need to do. We were trying to do some complicated things. This ends up being super simple, and it works really great. So discrete Morse theory itself is due to Foreman, and the idea is that you have your cubical complex. So it's not a filtration, just a complex, and you can simplify it. You essentially draw a bunch of arrows according to some rules, and kind of matching a face with its coface, or a cell with its coface. And at some point you will have possibly some cells which will be not matched with anything. They're called critical cells, and those are the cells which really tell us something about the topology or homology of this complex. So here we have a bunch of cubical cells, but after applying discrete Morse theory, we see that that this is really equivalent to a single vertex. So we know that adding this complicated structure to our complex is the same as adding just a new connected component. And it works like this also for higher degree homology. One thing which is interesting is that doing this, drawing those arrows in an optimal way, like it was done here, is actually NP hard in general for in particular for higher dimensional cubical complexes. But one really interesting thing coming out of this paper by Vanessa and other people was that for subsets of cubes in dimension lower than 3, this computation is really trivial and can be done in linear time. So in this very special case, you can do this simplification very efficiently. And then, so this is an overview of the algorithm. So the idea is that around each voxel you draw those arrows, which essentially simplify this kind of block, so that only in the end only the critical cells matter. So in this case here, there are only 3 critical cells. So one way of thinking about this is that you reduce it. You could think about this as some kind of filtered CW complex. So this is you could think that this gives you a much smaller representation of this filtration, which still has the same persistence. So here, from those many cells we have here, you can think that you realize that this is exactly as adding a single vertex at 1, then creating a loop around it at 8, and then killing off this loop at 9. Computational, you don't really think about CW complexes. In the end, you just cook up a boundary matrix, reduce it, and this gives you the persistence as usual. And one crucial computation here is to determine the boundary relations between those critical cells, and you do this by following certain paths along those arrows, and typically you just need to count them modulo 2, because we're doing, typically in persistence you do it over Z2 coefficients. So again, I'm not really trying to explain discrete Morse theory, but the main point is that in the end you get a much smaller boundary matrix, which still gives you the same persistence. And the crucial computation has to do with following those and counting those alternating paths, which are also sometimes called V paths. And if you do this carefully, you should be able to handle data of size roughly 500 cubed and maybe simple data of size something like 1,000 cubed. Maybe I could say that around 2012, I think, with Jan Reininghaus and David Ginter, we had a very nice, very thorough implementation of this, and unfortunately this got swallowed up by some commercial software those guys were also working on. So this would be really good to have, in 2012 and also in many following years, but unfortunately this was not public software. So this was kind of, like, in hindsight, this really kind of set things back in terms of what you could do with image data using persistence. But like I said, if you're not careful, this could still be very slow. And one crucial observation is that this seemingly simple idea of counting those alternating paths can go really wrong. And it turns out that in cubical complexes in dimension 3, you can have complicated behavior of those paths. So here, this would be one critical cell, and this is the other. We want to know how many paths there are between them. And here, there would be 2 paths. But now if I iterated this construction, if I glued this thing down below, I will be exponentially bumping up the number of those paths whenever I do this. And surprisingly, this is something which happens naturally in those computations on actual data. So if you're unlucky, you can have a long chain of those things, and then when you're trying to enumerate all those paths, the computation essentially becomes exponential. And so, and the underlying reason for this is that those paths can, in 3D, those paths can both split and merge, which is, which is perhaps surprising because they kind of model gradient paths in a gradient field, which couldn't do this. So one solution is something we did with Pavel Dwotko around 2012. This is actually unpublished. It's only on arXiv, I think. And it essentially turns this problem of path counting into a simple graph problem, and in particular a graph problem on directed acyclic graphs. And whenever you have this, it's a good idea to essentially just topologically sort it, and then you essentially just have to traverse this graph in this topological sort order, and then you can just propagate the number of paths. So in the end, this is a very simple algorithm. Here is a simple example where I counted there are 5 paths between this vertex and this vertex. In our case, we would count it modulo 2. So all the computations would be done modulo 2, and then you would learn that there is an odd number of paths between them. So in the end, this is a very kind of basic solution to this problem. There are also other solutions that people came up with, but this is something you definitely need to have. One example of software which implements something very similar to what I just described is TTK. So Topology Toolkit, they have this Discrete Morse sandwich method, which now I would say now it's quite comparable with this kind of loss implementation that I mentioned. Another software trying to do a kind of similar simplification is Cubical Ripser. Cubical Ripser doesn't do the simplification at the level of the cubical filtration. It rather does it at the level of this kind of implicit representation of the boundary matrix, similarly to Ripser, but essentially in the end the idea is similar, just to get rid of the essentially prune the part of the representation which only contributes to those ephemeral pairs. And if you do this, you get something which is, I would say, significantly faster than this kind of naive boundary matrix reduction, by maybe something like an order of magnitude. But memory tends to still be limited. So maybe you can push it until something like 500 cubed, but memory tends to still be a problem for this type of methods. And essentially the issue is that the filtration you may not be able to fit in the entire filtration in memory. So what can you do then? So the idea, which took me a long time to develop, so I had an initial kind of sketch of an implementation around 2015, and it got only published at Sausage at 2023. That the software has been available since like 2018 maybe. So the idea is that instead of loading this whole volume and cooking up this whole cubical complex out of this, you can kind of you can stream pieces of data from disk. So this is what you would have in memory at any given time. And then we can think that we process those things in slices, and that there are those kind of codimension 1 borders which are at the intersection of those slices. And then the idea is that you can apply this discrete Morse theory trick, by Vanessa, for each of the slices and borders independently. So essentially, you're building up pieces of information on the filtered discrete Morse complex, or more explicitly, you just need to know information about each critical cell its dimension, its value, and also boundary relationships between them, which you get by following those alternating paths. And well, one technicality is that this representation is kind of large, so you would store it on disk, and then based on this information, you would reconstruct a boundary matrix, and then again, once you reduce it, you get the persistence diagram, which is, the same as the persistence diagram you would get directly if you loaded the whole thing. So if you do this, so this is implemented in my Cubical software. So with this, you can handle, I would say, easily up to something like 2000 cubed. I actually did it on my laptop. It roughly takes an hour, and the speed for this, the throughput, is roughly 1 million voxels per second. So it's both. So it's the main selling point is that it's much more memory efficient. You can use much larger data that would never, fit using those standard methods. It also tends to be, I would say, it tends to be faster than most of the other methods. From what I've seen recently, TTK scales parallelizes very well. So on smaller data, TTK can actually be faster if you have enough cores. So I would say this is currently the fastest method, but it's definitely the only method which can handle such a large data on commodity hardware. It's not obvious this works. This requires some proofs. This method kind of uses a weak version of, I would call it, stratified discrete Morse theory. But the crux of this is that those alternating paths, which would, which could potentially span all those slices, they're essentially partitioned by introducing some extra critical cells, and this is kind of happening naturally. So all those alternating paths, which end up giving us the crucial information, they're contained within those individual slices and borders. And just like normally, each slice is significantly simplified. And one crucial thing, which was kind of a gamble of my part, was to implement it and then check if it works, in the sense that how many extra critical cells would be created around the borders. And if there were too many of them, they would dominate the computation, and the whole thing just would be inefficient. But it turns out that not too many of those extra critical cells are created, and typically those are exactly the critical cells which we need to kind of stitch this local information together. So in particular, the information about holes, or topological features which span the entire volume, they are encoded by alternating paths which would also span the whole volume. And one thing which happens naturally in this algorithm is that those individual alternating paths get kind of stitched together by those critical cells. So in any case, this final boundary matrix which we get out of this, it's small and still contains full information about persistence, including the information about those potentially very large features which may not be contained in any single of those slices. And recently, I want to mention this very briefly. Cubical was essentially re-implemented on a GPU by Fan Wang, who recently graduated. He was Chao Chen's PhD student, and now I see that the Chao and Chen are two people now, which kind of makes sense. yeah, it's fair to say that SHA works for 2, I guess. So I guess that makes sense. And so it follows the same basic. This implementation is on GPU. It follows the same basic principle, except doing those things efficiently on GPU is much harder. One thing I would mention is that each slice has to be additionally partitioned into what's called a block in GPU terms. So each of those blocks is a bunch of threads which have to work together. So essentially, you would assign one thread to each cube in this small portion, and then those threads essentially have to do the same computations, although on different data. So you have to really express your computations, that have to do exactly the same operation on many of those cubes. And many of the pieces of this computation can be done efficiently and easily in this way. The main challenge was to count those alternating paths in an efficient way. So Fan had to come up with a new algorithm for this, which includes coming up with a new topological sorting algorithm, which is kind of tailored for the type of graphs you get from those cubical structures. And again, this was kind of a gamble because it was not clear if this would give us any speed up, because we knew that this type of algorithm is not very GPU friendly. But in the end, with a lot of effort on Fan's part, it took like 13,000 lines of CUDA code, and it was 3 years in development. In the end, it seems to work well. You get up, I would say you typically get up to like 10 times speed up compared to Cubical. So with this, you can get something like 10 megavoxels per second throughput. So this would be like the newest improvement using GPUs. And so I will be wrapping up. So in terms of software that I mentioned, I mentioned Goody, which I think is great, especially for smaller data. It's very convenient to use. You can use, it has Python bindings. It's easy to use. You can get some extra things, which often you cannot get from other libraries. You can get things like representative cycles. You can also impose different boundary conditions, which is useful for data coming from simulations. For Like I said, Goody just does the straight up matrix reduction. So it has some limitations, especially in terms of memory for slightly larger data. Maybe in this range, I would definitely recommend Cubical Ripser. It's very convenient to use. It also has Python bindings. One thing I would say is that make sure you use the cripser package for Python. I've noticed that many people recently have been using the I think pyripser package coming from the from some other repository. And Cubical Ripser is really tuned for cubical complexes. The other essentially just forces Ripser to work with cubical data through some trick. So make sure to use this. For larger data, I think I would say currently the only viable option, if you have to work with huge data like this, would be Cubical. You can hope to get roughly 1 million voxels per second throughput. If you're curious how it really works, since I only spent like a couple of minutes on this, this will be the main reference for this. Okay, and as a real summary, I think if you work with this type of data and you do TDA, I think it's good to know that there are specialized methods really tailored for image or cubical voxel data. And and in many cases it would be a mistake to use some kind of generic method which is not specialized for this. So hopefully this is clear after this talk. During those last, let's say, 15 years, we went roughly from being able to handle data set with, let's say, 1,000,000 voxels into data sets with several billions voxels. So this is roughly 8,000 times larger data. And in terms of speed, we gained a couple of orders of magnitude, let's say 4 orders of magnitude in terms of speed. And now you also understand how at least some of the techniques which went into this, and none of this was rocket science, but it was really important to apply them roughly in the sequence and actually take all of them into account. Which I think is it's important that people are aware of this, because if you wanted to further improve on those methods but miss one of those tricks, chances are that the resulting implementation wouldn't be efficient. So I think it's really good to know what the ingredients are. And I think this is all I wanted to say. Thank you.
All right, so before we get to questions, why don't folks unmute themselves and let's applaud for the speaker. All right, questions. So there's one in the chat. Dylan, please feel free to unmute yourself. But otherwise,
Perfect. No, that's all
go
good.
ahead.
I'll unmute myself. Here we go. I don't think I can turn the webcam on. No, there we go. How we going? Can you hear me all right?
Yep.
Yeah.
Perfect. Thanks. Yeah, so that was a great talk. Thanks for that. I really
Thank you.
appreciate it. But I was curious, like at the start of the talk, you were obviously talking about ways of, okay, we have some cubical data, we could use cubical complex, or we could triangulate it, which may be a more naive way, and that might have some overheads. Is there ever a reason at the moment to not use cubical complex for 3D voxel data?
Yeah, that's a great question. The answer is yes. So like I mentioned here, those three are exactly equivalent, so it doesn't really matter which one you compute, you get the same information. This one gives you something else. I didn't go into this, but if we think of, if you just think about two-dimensional images, those two represent different type of connectivity between pixels. So this would correspond to what people call 8 connectivity. So each pixel is connected with all the 8 neighbors, and this corresponds to this kind of weird connectivity of 6 connectivity, where you have this extra diagonal, but not the other diagonal.
Sure.
And in some situations, you may want to use it, especially in situations where you're interested in some statistics, topological statistics. So one caveat to using this is that depending on which one you choose between those two, you will either have too many, you either have kind of, in your discretization, you will have too many connected components or too many cycles. And in some situations where, where this data comes from something, maybe some smooth process where like, for example, Gaussian random fields, which first of all are symmetric, and also how many components and how many cycles you want to get, and you also know that there should be roughly they should correspond to each other. This standard interpretation does not give you this. It is kind of biased towards either the components or the cycles. And one way of kind of breaking those type of ties would be to change to this different connectivity. And you can either do this, inside the software, or you could cook up a slightly larger image, which would essentially kind of simulate this type of connectivity. And enlarging your data by some factor seems bad,
Yeah.
but with those methods like with Cubical, it would essentially have no impact on the performance, because it would be just a larger data representation, but there wouldn't be more. It wouldn't be more topologically complex, and essentially those methods scale with I would call it topological complexity, or topological complicatedness of the data. So essentially how many non-zero persistence pairs you have, and by cooking up this slightly different input, you wouldn't be really changing this. So so playing tricks like this is viable with this new software, and would probably not be a good idea 10 years ago.
Yeah, sure. I see. Well, thanks for that.
Mm-hmm.
So, Hubert, I have a question, and I'm going to phrase this as an analogy, and I expect this analogy is wrong, but please correct it for me. So, like for the um, linear programming, right? You have the simplex algorithm, which is exponential in the worst case, but in practice is much better than, these polynomial time algorithms, right? So persistence, polynomial time algorithm. Now to make it efficiently computable, yeah, as you mentioned, there's a lot of discrete Morse theory ideas that you need to implement well. And you described how you could get, in the worst case, sort of an exponential number of alternating paths,
Mm-hmm.
right? So is this a reasonable analogy? Like in the worst case, if you're using some of the discrete Morse theory tools, they could be exponential in the worst case, but in practice, they lead to really important speedups. You're shaking your head.
No. So it's yeah, it's not a good analogy, but it's good you mentioned this, if this was
Okay,
confusing. So
perfect.
so if you kind of implemented discrete Morse theory naively, the analogy would be perfect. You would just really hope that this type of motif is not repeating too often, because if it does, it would lead to exponential complexity, or at least exponential in some parameter, which could be as large as your input. But this is in the end, this is not really an issue, because and the insight is that you don't need to enumerate all those paths. There can be billions of them, but with very simple techniques, you can count them. And counting in this case is much easier than enumerating. So you can count those exponentially many paths with a linear time algorithm. And I mean, in general, to really count them, you would need some large integers, which would kind of go into the complexity. But here we only need to count them modulo 2. So it's really a completely, at least in theory, this is a completely straightforward linear time algorithm, which solves this seemingly exponential time problem. But it's not really, because we don't have to enumerate all those paths. We just count them, and this is a simple linear time program, or algorithm.
I see. So persistence is still like polynomial in theory and in practice, and even the best speed up tricks still keep this polynomial worst case. Yeah. Okay.
Yes.
Perfect. Cool. Thank you.
If this was unclear, it's really good you asked, because it wouldn't. I definitely don't want people to think that that there is something exponential lurking in those implementation that could, wake up and, eat, 100 years of their computations or something.
Mhm.
I mean, there is another kind of potentially exponential thing, which is again not lurking there, is this computation of those discrete Morse matchings, which happens to be much easier in dimension 3 and below. So if there was quite a bit of work in general cases for computing those discrete Morse matchings. So you may, some of you may be familiar with some kind of pessimistic results on this, but this is a really nicer case. So in a sense, a lot of things, it's the setup is kind of complicated enough to potentially cause problems, but at least and in dimension 3 and less, everything ends up being really nice and simple.
That complication in higher dimensions is surprising to me. Yeah, I'd like to learn more about that. So.
Yeah, so I mean, so yeah, this is interesting. So I learned about this from this paper by Vanessa that I mentioned. They cite another paper where people really looked at those things, and it turns out that I think already in dimension 4 you can embed, I think, Bing's house as a subset of a single, as a subset of faces of a single, of the boundary complex of a single voxel. So they can
Nice.
so you can get topologically things which are kind of topologically harder to detect as a subset of those cubical complexes, which leads to problems with getting a perfect Morse matching, and then so this is about getting the perfect matching, but also there are some algorithmic problems because of how complicated those things can get. So things, it seems that things, if you wanted to apply this directly, things get kind of wild in higher dimensions.
That helps. Further questions, comments? All right, well, let's call it quits for today. Thanks so much.
Thank you.
Bye-bye.